All right. Well, good evening, everybody. Clearing my throat there, something I probably could have done while that entire introduction was running. Well, greetings, citizen scientists of this great big world, wild and wonderful world in which we live. I, as always, am your humble science communicator, the Great Orbax. I'd like to welcome you to the first show of our summer series for the Guelph Physics live stream. Yes, as always, we are located here in Physics Hollywood, in Guelph, Ontario, Canada, on campus, broadcasting out to you. And we've got a pretty special show for you tonight. We're going to be discussing the science of batteries with two of our own, Guelph Physics alumni leading up to it. And speaking of alumni and incredible segues, you might notice that below me, running across the bottom here, is an announcement. I want to announce that we will be having on June 25th, we'll be having a Guelph Physics alumni celebration. Yes, that's right. Look at that. Right there. So at the end of this month for Alumni Week, we're going to be celebrating our 125th plus one year of Guelph Physics here at the University of Guelph. So if you join up and register, it's a registration is free, done through Alumni House, and it'll give you an opportunity. We have invited speakers for the day. We'll be talking with Dr. Dennis Mooker, who will be discussing his proton therapy treatment for cancer with X-ray or with proton rays. We're also going to be talking to Scott Van Bommel about life on Mars and the possibility of finding anything up there on that planet of robots. So we'll be having those discussions as well as a chance for social interaction that'll be taking place. All of that and more taking place on June 25th. So please join us if you can. You can check out Guelph Physics website as well, and we'll have links to all that information there. Now, without any further ado, I don't want to go too long without introducing our wonderful guests and starting our panel for the evening, but I did mention one of the things that we're going to be discussing tonight, and the major point of interest for tonight, is the idea of talking about batteries. So, in 1780, in Italy, Luigi Galvani took a pair of frog legs that were hanging from metallic hooks and found that when probed with a piece of metal, that those would actually twitch. And he believed he'd discovered something that he would call animal electricity, a form of electricity that was stored within the muscles of the frog's legs and be could utilized after those legs were, well, removed from the actual frog itself. His findings were doubted by one of his colleagues, Alessandro Volta, who believed that the flow of electricity they were observing was actually coming from the mismatched alloys of the hooks in the actual metal probe. In order to prove his point, he found that if he stacked layers of zinc and silver and interspersed them with salt water, soaked cloth, and paper, that you could observe a flow of electric current from the wires that are attached to the ends of the stack. By doing this, Alessandro Volta created what would be popularized as the world's first battery. Now, the question as to whether it was actually the world's first battery or not is up to some debate. There's rumors that ancient civilizations as far back as 150 BC had perhaps harnessed the power of early batteries for things like electroplating, using vinegar as an electrolyte and copper and iron as electrodes. But it's unclear as to whether that's ever actually really happened or it's just a legend. Regardless, we have Volta's creation in 1780 on the record as our first battery. And later, he lent his name to our individual unit of electric potential, the LS. That's a little joke about voltage there. Of course, it's the volt. I'll see myself out there. Very good. Okay. So, without any further ado, we can probably assume that battery research has come a long way since poking at dismembered frog legs, but our panel tonight will be able to verify that and fill us in on all of the excitement of the world of battery research and what is to come from there. So I'd like to welcome to our discussion our panelists for this evening. Joining us is Dr. Mike Fleischauer, as well as Dr. Stephen Glazier. Hello, doctors. How are you doing today?
Hello. Doing well.
Doing pretty good.
Fantastic. Now, I assume we've come quite a long way since poking at frog legs in terms of actually talking about batteries and battery research. And I wanted to really get into this idea tonight about what is current. I just came up with that now. Can you believe that? That type of incredible wit. I wanted to talk a little bit about that, but we've got a whole idea for the discussion tonight. We're going to talk a little bit about your journey from Guelph into the world of batteries. But I wanted to start by asking a common question to both of you. And I guess I'll start by asking Dr. Fleischauer, if you were to tell a physics undergrad student or an alumnus, about the most exciting thing about battery research, what would you tell them?
I think the most exciting thing overall is that the whole field is exciting now. Like it used to be, 25 years ago, it's, oh, I'm doing batteries. Oh yeah, so anyway. And now there's a lot of people are really seeing the potential of it. It's in their everyday lives. And so the opportunity to translate what we're doing in the lab or in undergrad back to the real world is pretty, it's probably the best part of the job.
That's such a huge thing, how accessible the concepts of batteries are now. And I want to get into that. And I want to talk about that a little bit later, because you're right. The modern world and people within even just the last, maybe even 2 generations here, the difference in how they view battery technology has fundamentally changed. Dr. Glazier, I'd like to ask you the same question. The most exciting thing in your mind about battery research that you could tell an individual who wasn't a super battery nerd already, what would it be?
I think it would have to do with kind of the whole green push, the renewable push, and just being at the center of everything happening. Especially in my role, I'm kind of in the heart of industry. Working on existing technologies and making them cheaper, greener, more accessible to the industry. And it's just you can see it every day. Like we can't keep up with where things are going, and it's really exciting to be part of that push to this next, the future that I hope we're heading towards. So yeah, and it's if I can just go a little bit further on that, one of the more exciting things I think for me is something that's underlooked a little bit, which is because everyone's focused on EVs, it seems. Electric cars and Tesla, it's, super flashy. But for me, it's grid energy storage. That's, the really big, exciting thing. It's, not as flashy and sleek, but, it's the thing that's really going to save us in the long run.
Well, that's exciting. These are, there's a lot of ideas that we can really get into with this that I think are going to sort of change, that we should really change the way that we think about batteries and how this all works around. But you mentioned this, Stephen, and I want to get into sort of the perspectives that you're both coming from. Dr. Glazier works for a company called Novonix, and if I'm reading your bio that you sent me correctly, that company develops high-performance, low-cost battery materials and provides consulting and technology development programs for external clients. Your role at Novonix is to enable faster adoption of affordable, high-performance battery technology across the battery market. So you're joining us from the heart of industry in a company that's focused on trying to make better, more reliable, more sustainable batteries. Dr. Fleischauer, you're joining us from sort of the academic side of this. So you're currently working now at the National Research Council for the Nanotechnology Research Center in Edmonton.
That's right.
You're also on the City of Edmonton's Energy Transition Climate Resilience Advisory Committee now as well. So we've kind of got these 2 different parts of looking at battery tech and where it's going from the private sector and from our national research side. So I'm excited to kind of get into this. But here's the big question, I guess, to start with for this whole thing. And it is this: how does a battery work? Now, I don't want it to overlook the obvious, but I think some of our viewers probably don't even know the basics of how a battery actually works. So, Dr. Glazier, since you sell these things, tell us how it works.
Sure. I guess starting from the very basics, you have your positive and negative electrode, which in industry we more say it's not very physicsy or chemically correct necessarily, but we say the positive electrode's the cathode, the negative electrode's the anode. We always just refer to them as kind of stationary, cathode is always the positive electrode kind of thing. But yeah, so your cathode and your anode. The cathode is where all the lithium starts at the, when you create a battery or a lithium ion battery. And so it's kind of hosted in this material, so in the cathode crystal structure, and it's kind of happy there and wants to be there. So when you charge your cell, you're pushing electrons through your external circuit, the lithium ions to have charge balance move over to the anode, and then that's where the charge is stored. And then it doesn't necessarily want to be there, so your energy is stored there. And when you let electrons flow back through the circuit and do work, your lithium ions move from your anode over to your cathode, and that's if you just do that reversibly over and over. And both of those structures can have to host the lithium in a electrochemically stable way, so that you can have this reversible process for as long as possible.
Well, and I guess that's kind of the sort of two basic ideas that I can see as what pushes battery tech from somebody who's not involved with it at all. When I talk to my first year students about what a battery does, I talk about this idea that it basically boosts the charge, that you can have a particle that comes in and it gets more energy, and that energy is propagated along that electron chain, delivering it to the things in that circuit. But physically, you actually do have chemical motion of the ions that are within that battery. Dr. Fleischauer, do you want to speak to that a little bit?
Sure. I thought Stephen explained it well. We're most of the stuff that we're working on to take it slightly more focused on the material side than what's the bigger picture for industry is we're trying to move lithium. We're also working on lithium ion between one electrode and another. And one of the questions we're trying to answer is, what does the local structure around that lithium look like? How does the lithium arrange itself in each of the electrodes? So when it's got a different arrangement, that's a phase transition, just like a crystallography type thing that I started in undergrad way back when. And so if you have different crystal structures, you have different potentials. Those different potentials are how you actually store energy. By moving from one phase to another is how you actually store or release energy inside the cell.
Neat.
Yeah.
Well, there's just so much that there is to discuss about this. And I guess you're both working in the fields of lithium ion batteries, but there are other types of chemical structures that create batteries. I mean, you can even, from what I've read, you can even literally just put a hook in a frog's leg and probe it with a different thing. And it'll cause we've done, lemon batteries and stuff as well. Is this idea of the lithium ion battery, how recently was this kind of come across that this is the ideal structure to move forward with for battery research?
Stephen, do you want to take that or want me to?
Yeah, I mean, I can speak a little bit to it and then pass it over, I guess.
Sure.
So I think, it was kind of in the late 80s, I guess, where a lot of the initial research was going on about this. And then in the 90s, I think the first kind of lithium ion or metal type battery was commercialized. And since then, a lot of work has gone into other types of electrochemical cells related to that. This like sodium ion or even like potassium ion. So these metals, and the best thing I guess about lithium that's really made it so accessible is the energy density you can achieve with it. With lithium being so small, it can really, you can make structures that host lithium really relatively easily, whereas all these other ions are just so big that it's hard to get these structures that will host it reversibly and that are also kind of feasible to move forward and get the energy density and the lifetime that we really need to move forward. And some of the other aspects, like the electrochemical potentials that some of these things are stored at, aren't really feasible to get required energy densities for specific things. So lithium ion is kind of this happy marriage of we can get enough lifetime and we can get we can make the structures for it and things are relatively stable. There's a lot of work still to go to make things even safer and cheaper. But it's kind of, for now, this thing that works most places for most applications.
And so was this the major breakthrough that sort of took us away from the traditional, what I, as a person who's not involved at all, would think of as a AA battery or AAA battery, the classic, I pull it out of the junk drawer with 15 other ones of the wrong size for whatever device I need and find the encrusted acidified ends of it that I'm now not sure how to even throw it away. But there's a basic difference between that structure of battery and then to the lithium ion. So you're saying that the lithium ion, that was the major breakthrough to sort of take us to that next level from where AAAs, AAs, what we would classically look at were. What were those made of? What is the major difference? Is there a lack of electrolyte in the lithium ions? Is there a different, clearly difference in the material? There's no lithium in the previous ones?
Right. Not in most of them. I think the Energizer lithium, or actually they do contain lithium metal, but that's a relatively new development that's come out. I think the initial ones are mostly manganese oxide with a potassium-based electrolyte. It's all a question of how much you're willing to pay and what you want it to do. So the big breakthrough for lithium ion is that it was viable to get a whole lot of energy in a relatively small package, and I don't think you'd want to have to replace 20 or 30 single-use cells in your laptop each time. You couldn't get a nice thin package. You couldn't have you remember the old cell phones back in the day where it was about the size of a brick, and that was with a rechargeable battery. Imagine having to take the cells out each time. It's not really a good use case. And in a situation for a car, you're looking at maybe lead acid or something else. It's a challenging thing.
Yeah, I mean, that's the interesting thing, is because when I think of a car battery, I guess I'm probably from the last generation, like Dr. Fleischauer as well, of pulling out a battery out of a car and making sure that you weren't spilling it because it was just full of acid and electrolyte, right? So, I mean, is that kind of, I mean, I guess clearly the transition is twofold. You're looking for higher energy output, but you're also looking for something that, from an engineering perspective or structurally, is just safer, more efficient, and you can jam more of them in there.
And I think we should probably make a note to really strongly discourage anyone from pulling their rechargeable battery out of their car. Don't do that. There are a few people that know how to do that, but that's their full-time job, and they have very dedicated facilities. So,
well, before we get too far into the specifics of how you would recommend young people take these batteries out of their electronic cars,
I don't.
Never.
I'd like to point out another thing. We're chatting here live, so if you happen to be watching us live right now, feel free to ask questions in the chat. They can come up automatically, and we can bring them up. So if you have any questions for our doctors, please just throw it out there for them. What I would like to, before we get too deeply into the actual science of the batteries themselves, I'd like to talk a little bit to our panelists about their journey and what brought them to it. I mean, I know that we have undergraduates and potentially recent graduates even just hanging about, getting ready to come on later on, but watching. And I'm curious, you know, a lot of our students have a difficult time sometimes seeing the forest for the trees and understanding that there's life beyond fourth year physics and the path that leads them. We'll start with Dr. Fleischauer. I mean, when you graduated in 2001, I believe.
Yep, 1 year after you.
From the University of Guelph. Yeah, that's right. You were in what I like to call the start of the Age of Enlightenment, 1996. When I became part of the undergraduate students here at the University of Guelph. But, you know, at the time, I would never have pegged you as a battery nut or somebody who would potentially even get into batteries as a field of research. What led you to that world? And walk us through where you kind of went from undergraduate to where you are now.
Oh, sure. So I think that I didn't know what I wanted to do, certainly at the beginning. I've always had an interest in the material side of things, not just from engineering how to use them, but what's happening inside. And I really particularly remember a fourth year lab at Guelph that had X-ray diffraction. So we were putting an X-ray beam inside of back in the day, we had copper pennies and pennies. And by shining this X-ray beam into the penny, we could actually detect that it was made of copper. And I thought that was really, really interesting. I was looking around for what to do after undergrad. I was thinking about graduate school. I was already going out to Dalhousie, and I met a prof there who said, okay, we've got this technique that we're interested in doing. There are this many people that are interested in it and this many people that are doing it. I'm like, oh, and it involves a lot of X-ray diffraction, and that's kind of how I got into it. Once I got there, I got interested in the batteries that's what the lab does. So Stephen and I did our degrees in the same group, and Professor Jeff Dahn, like a very strong battery researcher, arguably the strongest in the country or the world. So then I was kind of seeing what's possible with batteries. I then got really interested in energy policy, energy use, and how we can actually make a difference on it. And that's my career has kind of flowed from there.
Well, it's interesting that sort of a rare chance or an opportunity to do a lab in undergrad actually led to a career from that. And it's also a kind of an interesting thing, because I followed a somewhat similar path where through undergrad, you don't get much of a chance beyond just your undergraduate labs to actually work with physical materials. Yeah. And the material properties and the material elements of stuff was something I didn't even really consider as a potential for graduate work until I did my fourth year project. So it's interesting that so much of physics is stuff that we don't even necessarily touch on in our undergraduate studies.
I think the challenge though is there's so much stuff to do, right?
Well,
it's hard to pick on certain areas to focus on. And I think it's good that you have the broad background. I'm not saying you're going to use every single class in third year and fourth year, but it's nice to get the exposure to the various things. And I actually still use a lot of what I learned in third year and some of what I used in fourth year in the fairly day-to-day stuff.
Amazing. Well, let's bring in Dr. Glazier as well. So you graduated, am I right in saying 2013? And so you came from a later graduating.
Did we lose him?
Well, I guess so.
All right. Well.
So you came from a later graduation class?
Yes, I did. Quite a bit later. Yeah, and I think my story starts slightly similar. I really didn't know what I wanted to do. I actually had I was working with as a summer student for Datong Zhang, and I remember having a discussion with him because I came out here to talk to a few profs at Dal in both the physics and the chemistry department, kind of on the renewable energy stream. And I talked to Jeff Dahn, and I didn't really know much about him. And I came back and I talked to Datong, and he just kind of like, I'm pretty sure he like smacked his desk and he was like, "You should go work for Jeff Dahn." It's like, he's this big, huge name in batteries, and you should do that. And so, I came out here and did my master's with Jeff, and that was in the material synthesis side of things, working on cathode materials, a lot of X-ray diffraction. I went to the Canadian Light Source and did some X-ray absorption there, and then did my PhD in doing ultra precise calorimetry on cells and trying to measure the very small amounts of heat flow off of cells from parasitic reactions or for unwanted reactions that ultimately lead to capacity fade and the eventual cell death, so to speak. So yeah, I kind of to what you were saying, you kind of apply all of third year and fourth year, from thermodynamics was a huge part of my PhD, to quantum mechanics, doing quantum chemistry to kind of understand certain transitions or certain reactions that would happen in these really complicated systems. Even to circuits, looking at electrochemical impedance spectroscopy, building circuits that have real and imaginary out of phase and in phase impedance components. Everything is applied in batteries, and it even starts to challenge your chemistry knowledge. And I think most physicists, when they hear chemistry go, ugh. But it's batteries is just this like great place where physics, chemistry, and then eventually an industry like engineering comes hard in and brings everything to life.
Yeah.
So it looks like we're back. We'll be coming back.
Hi. I think the real question is, do we need them? So, so we got some questions in the chat. Stephen, I don't know if you can see them. Talking about supply issues in the near future. I know there are challenges with lithium supply all over. I know there's many different bottlenecks. There's like the cobalt bottleneck, which I don't know if you directly, but a lot of people I think in your team have been pretty involved with solutions for that. The cell manufacturing is a whole nother thing. I think Novonix has been working on. I will do a plug for Alberta because I live in Alberta now, and there's a lot of lithium resource in our oil and gas wells. So there's, I think the supply issues will exist. It's a question of how permanent they're going to be. One of the things I really like, even though I'm working at the National Research Council and I'm also an adjunct in physics at U of A, on one hand, it's really, really academic, but on the other hand, it's still part of a broader, very competitive market, not just on the research side, but the things we're doing have to be relevant to industry. And then it has to be relevant to consumers at the end to make it. Where do you think the supply issues are going to go in the next few years?
Yeah, it's going to be really interesting. Even the more abundant supply, the more abundant minerals and things for batteries are at a crunch right now because of the huge push. The price of nickel and manganese are still, sometimes a little constrained, and so getting those, people are looking at 5 to 8 years out in supply contracts for some of these materials in the industry because it's just it's going to grow so much. So hopefully, hey, Orbex.
No, I take some of these comments personally when I hear them. I was stricken down here by the internet gods at the university, and now I'm back. But they're saying that it almost seems like people seem to be happier that I was gone briefly. This is upsetting to me. Now, I assume nothing radical has been changed in battery development since I left and have now returned. Perhaps where are we sitting at now in the conversation? I'm sorry to have to insert myself back in.
Supply constraints.
Yeah, we're responding to the comments.
Oh, fantastic. So, Stephen, did you get a chance to instill some faith in our undergrads about your journey towards where you are now?
I think so.
Fantastic.
Yeah.
Good.
And one thing we could say is that our need to pivot because our host wasn't there is kind of the way a physics career sort of goes, but then hopefully have the tool set that because you're not necessarily an expert in anything, you're able to pivot. Like, how am I going to try to host a show, for example?
Well, I mean, here's an interesting thing. We might as well just jump into some of these questions. Did you guys talk about this idea of using seawater?
Yeah, I think it was kind of in the vein of the question we were talking answering about the supply and demand issues. Like lithium is going to be one of the major constraints moving forward. Just getting a reliable, sustainable source of lithium. There's a lot of issues with where lithium comes from right now and where it may come from, especially in terms of conservation issues, in terms of land use.
Yeah, absolutely. This is actually a question I had for Dr. Fleischauer before we started, and I might as well use this as an opportunity to insert it again. This idea of probably one of the things that makes lithium-ion batteries so sort of intriguing and interesting is this idea of using them as rechargeable batteries, having this ability to put energy back into them that can again then be taken out. And I mean, our society now has moved to rechargeable batteries for practically everything, whether they're phones, computers, your vehicles, and whatnot. But at what point are we're looking at the environmental impact is of a rechargeable battery versus a disposable battery? because clearly disposable batteries could be used and thrown away over and over again. The rechargeable batteries are perhaps made using techniques that maybe have a larger environmental impact with the mining for heavy metals and whatnot. Where are we with that, and how do we balance that?
I think the big thing is that it's not just rechargeable batteries versus primary, like single-use batteries. It's people are going to consume power. It's coming from somewhere. What's the environmental cost of oil, of gas, of nuclear, of hydro, of wind, of solar, all those things. So it's a question, I think, where batteries have a real advantage is that they're not converting a core fuel into something. It's the temporary storage thing. So I think the real things batteries are competing against are like renewable natural gas or hydrogen, different but similar things. That's kind of the long-term competitor. It's like, what's the best way to move a lot of power or a lot of energy?
Interesting. Dr. Glazier, what do you think?
Can you repeat the question?
Well, just what's the trade-off of the environmental impact between looking at something like lithium ion batteries versus even single-use or disposable batteries?
Oh yeah, and I think that's it's even a debate that you kind of see all over the place.
Well, I'm not trying to be controversial. This is gotcha journalism here, but it is something that struck me as it becomes, especially as you mentioned earlier at the beginning of our discussion here, this push towards green. It's something that people think about more than probably they thought about. I know when I was a young person, we didn't think about it at all.
Yeah, I think it's something that I struggle with in the battery sector and seeing batteries being used for everything. There's a lot of things that people are starting to use rechargeable batteries for that are like solutions to problems that never existed. And I think that's one of the struggles that I have with putting energy storage where it's kind of a waste compared to like some of the bigger challenges that we're facing. We really should be making sure that rechargeable batteries are being used for things like grid energy storage, for electric vehicles, and for maybe things that that also consume gas or carbon fuels, but with an emphasis on doing it well and for a long time, rather than kind of there's a lot of lithium ion tech that is made kind of disposable, not with a lot of care, just to like get in on the latest things like wireless headphones, for example. Like it's they're cool and they're handy, but do we need to make a billion of them worldwide every year? Like little things like that as an example. I'm not trying to bash wireless
on me.
Well, and it's interesting as well because there is this level of tech waste that we never had before. You even want to look at something as simple as how many laptops does a person go through their life in the last 10 years compared to the 10 years before that, when I had one laptop that I got in my grad work that I used for literally a decade. And now, I'm as bad as anybody else getting updated technology and things like that to do these incredible streams, which you're all welcome for. Now, speaking of young people who we're out of touch with, as many of our longtime viewers know, we have a roving reporter on the street who previously used to give us their undergraduate opinion on a lot of these and bring undergraduate questions to the table. However, now she's actually bringing about a month worth of graduated insights with us as well. So I'd like to welcome to the panel our roving reporter, Mel.
Hey.
Hello. Okay, I'm unmuted. Perfect.
I took the impetus to unmute you, as unfortunately I normally let you just go being muted.
Yeah, I never learn, even as a graduate.
Well, congratulations on your recent graduation. I'm sure our viewers are very excited for you. And it should be pretty interesting. I mean, we'd like to get some of your insights. What comes to your mind as soon as when you're hearing these types of discussions about batteries and energy storage?
Yeah, I'm definitely still like in that undergraduate mind, and I'm thinking to myself, like, even if I was just starting, I don't know if I would know what grid energy storage is. So if Dr. Steven, if you could talk a little bit about that, especially since you think that's, where things are going and that's the coolest thing. I want to hear more about it for sure.
Sure. Yeah. So grid energy storage, or stationary storage, sometimes called ESS. That's the reason I'm excited about it is, as we move to renewable energy sources like solar, wind, I'm missing something here, but yeah, solar is mostly solar and wind. We really need somewhere to put it because the wind's not always blowing, the sun isn't always shining. So, we can't just have it, harnessed and to, use live. And then when there's no sun or no wind, the energy needs to go somewhere. So grid energy storage is really focusing on making those technologies more accessible. So now that solar, there's been some huge advancements in solar technology, huge efficiency gains. The technology is really getting a lot cheaper. So we need somewhere to put that energy. And in order to do that, we need long lifetime batteries. We can't be making batteries that only last a couple years in huge amounts in these, huge fields of storage. They need to be stable at high temperatures. So when the sun is shining. They need to be stable over various use cycles, dumping all their energy into the grid when there is a huge peak demand or an emergency or trying to feed another piece of the grid. So grid energy storage is where it's at in my mind, but it requires us to overcome some of the traditional big issues with battery lifetime. But what is kind of exciting is it's not so focused on increasing the energy density as much. Like with a car, we need to get a lot more energy into a smaller, lighter package. But with ESS, most of the time, it doesn't matter how big the battery is, just that it will do its job and last as long as possible while still being cheap and, not more environmentally friendly to manufacture than the fuel that it's going to offset.
Well, and that it's interesting, and that's what a lot of your research is involved in is seeing how long you can store power in these batteries and how long before they start to lose the ability to store power in them. I know, Dr. Glazier, you were recently involved in this so-called this million mile paper, this million mile electric battery. Can you talk to us a little bit about that?
Yeah. So the million mile paper kind of combines a lot of technologies that, it just kind of shows how far lithium ion batteries have come, I guess. Just by doing, small changes to existing technology, the cathode material that was in it is not a brand new material. It's something that's, commercially available technology. The anode is graphite. It's used everywhere in most commercial lithium ion cells. And the electrolyte is something that Jeff Dahn is known all for electrolyte research, as well as actually kind of pioneering the NMC cathode, which was in this cell, and his work on the graphite anode. So he's kind of had work in all of these things, and to kind of see all of that come together in a fairly commercially relevant cell design that's has the energy density and kind of cost structure to be in electric vehicles, and then last thousands and thousands and thousands of cycles under pretty harsh conditions. It was kind of a neat piece of work to be involved with, to show all of these things coming together in a real cell made with traditional manufacturing techniques that works and can do everything we need it to.
Well, and you're speaking of these kinds of extreme, sort of the extreme pressures, the extreme circumstances that these things can go under. The first time that the lithium ion battery kind of came to a head, what I found out about it was in the news when they were exploding and catching on fire all the time. And Dr. Fleischauer, you work primarily with this idea of putting these things under stresses. So high heat and temperature, low temperature, pressure. How can you speak to us a little bit about that and what's involved with these and why, like, our battery? I mean, clearly, the idea of heat and cold makes sense in terms of a battery being able to live and to give us energy back. But pressure, what's involved with the use of pressure, and why would any of these things be undergoing squeezing or expansion or contraction?
Oh, well, there's a lot going on inside the battery pack, and then within the battery pack you have sometimes thousands of cells that are all about the size of your thumb or bigger than a AA type battery, maybe a C-size battery. Each time you're moving lithium between the electrodes, the cell expands and contracts slightly. And when you have those changes in volume, you also have big changes in pressure. Pressing the electrodes together, that pressure can be up to normally about like a megapascal, give or take. As the battery ages, you can get that pressure building up over time. So you can actually have a fair bit of pressure just within the cell. And that's just in a normal standard environment. And then we've got other harsh environments. I started off doing started off recently doing batteries for oil and gas drilling or geothermal drilling, where they've got really, really high pressures. But then you also have to think about like the short-term pressure, like what happens in an accident. If your battery is getting compressed, you've got lots of pressure buildup. What's going to happen in that case? So there's a lot of dynamic environments that you need to be able to deal with in the real world. Not so much on the grid storage side. Hopefully that's stationary and safe, but you'll still have pressure buildup within those cells as they're operating.
Yeah, I mean, it's funny that's not even stuff that I would have ever even thought of. Coming through with this as a thing. We got a question here from the chat, which is actually kind of on point. And I'll bring it up, especially now that we have Mel here, and I'll bring this up. We have a question for students, current undergraduate students in physics and nanoscience. What's a pathway towards getting into the battery technology field? What would you recommend for these undergraduates to do, and how can they move forward if it's something that they're kind of really interested in? We'll start with Dr. Glazier.
Oh, okay. Sure. The first thing that I would say is start talking to profs. If there's no professor at the university that you're at that does any research in batteries, you can always start reaching out to other universities. Never be afraid to start reaching out and talking to profs. That's how I got involved with research. My second year, I talked to Dr. Martin Williams and got involved with academic research.
And you're still talking to him now, probably.
Yeah, I wonder if
this conversation never ended.
Yeah, and just start talking with everybody. If there's no one that you can really that's accessible that does direct battery research, start getting into material-based research, like Mike was saying. Get into techniques that are used. Tons of X-ray techniques are used in lithium-ion batteries. Get involved in electrochemistry. Start looking at things that you're very interested in or courses you really like, and Google that plus batteries, and you'll get oodles of papers. Thermodynamics, quantum, like anything you want, and you'll get a ton that you can look at.
It's interesting. You bring up a good point, which is just to talk to people. I mean, the people who are researching this stuff are doing it because primarily they're interested in that stuff as a research. So if it's something that you're interested in as well, I mean, I've never met somebody who doesn't want to talk about their work, sometimes to an excess. But they'll always be happy to find people that are interested. Mike, do you have anything to add to that?
I think the only thing is that, I think physics is a really good background to get into it, but it's not enough. Like, the thing I like about the battery field is that you can't do it all on your own. Like, I took it as a great compliment when I was called a pseudo-chemist by a real chemist, because I've learned enough chemistry over the years to be like, okay, I don't understand a lot of these things, but from a physics perspective, here's how I think of chemistry. And, sometimes that upsets the chemist, and sometimes that's fine. But it's knowing, okay, here's how a chemist is going to view this same thing. Here's how a physicist views it. Here's how an engineer is going to view it. but then you need to be able to adapt all those different things together to actually move forward. There's the whole manufacturing side of it. That's another whole really complicated, totally different side of engineering than what you do for the engineering on how do I make this test repeatable.
Well, and I also think that there's a huge thing that, especially as physicists, is not always our primary concern, but it's communication, and it's being able to speak to those people in the industry in the language that they can understand and that you can understand from them. So I think it's a vital thing as an undergraduate as well to be able to communicate with people in different disciplines and different fields and be able to understand that. Mel, what's your insight here?
Yeah, I mean, I definitely agree. I think networking with people in the department and other departments helps immensely, and also like volunteering and your time and like getting involved, it helps. But I do have a question. Mike, you mentioned that there's some courses that the knowledge that you learned, you still use every day. I think as an undergraduate student, they have some like choice in what they want to choose in their like fourth and third year. So what were those courses for the students?
To get this straight, you're not calling him a liar. You just want him to back up his previous statement.
Yeah. I mean, I'm interested in what courses are the most helpful in this field.
So last summer we didn't have lab access, and normally we're very, very experimental. I'm quite good with a lot of different wrenches, unfortunately or unfortunately, and we didn't have lab access, and so we switched to modeling. And I was relearning a lot of my partial differential equations, and it's probably a gross oversimplification, but my general view of electrochemistry is there's a very simple rule, fixed law at the beginning, and then most of their equations derive from that. It seems, from my perspective, that a lot of electrochemists, which is a very hard field on its own because it combines physics and chemistry, but it's separate again. There are a lot of simplifying assumptions. You start off with fixed law, and then you get to some equation, different assumptions, different equation, and so on. What we're trying to do is we're not working in the conditions where you can make the simplifying assumptions. So it's like, okay, let's actually do this from the very beginning. Let's go through. So differential equations, a big thing. Right now, one of the bigger problems that I'm stuck on is how to do better optics. We've got an image that we'd like to just zoom in on, and I want to buy a part that can do that. The problem is I need that part to be about 8 millimeters in diameter and able to withstand 150 degrees Celsius and. I don't remember how to do the optics design. Circuits, super simple thing. Stephen mentioned electrochemical impedance spectroscopy and doing the modeling on that. That's a big thing that we're working on now. And how do we get reliable, repeatable measurements with impedance spectroscopy? So it's all, fourth year was a bit of a blur, honestly.
Yeah.
I can remember a lot more of the third year, and it's like, yep, this stuff's actually pretty useful. I don't do quantum right now. I don't do general relativity. But the more hands-on courses were actually, and like optics, circuits. I don't use a lot of my advanced mechanics, but the simpler ones, all the time.
Stephen, are there any courses that you took at undergrad or things you remember from your graduate work even that push forward?
Yeah, I think, from my graduate work, thermodynamics was a huge one, but, just in terms of, kind of the fundamentals behind why things like how, some of these phase transformations occur is kind of all rooted in thermodynamics. So that's a huge one. Circuits is a great one, but one of the, I think I might even, StatMech even. So everything comes down, like it's every course, like quantum, in ways that you might not even think it's fairly relevant, but it's more quantum chemistry, but even still, quantum chemistry, if you've taken quantum in a physics curriculum, it's much easier to understand. And people do kind of these models of how these reactions happen in these really complicated systems. And the only way to do it is with quantum chemistry and these huge complicated calculations that take massive computers weeks to do. So yeah, I mean, one skill though that I'd really encourage everyone to learn is how to do basic scripting for data analysis. That's something that was a huge asset in analyzing battery data, because there's a lot of it's a lot of information coming from the cell, and you can tweak it in many different ways, in some ways that aren't standard. There's a million ways to analyze cell data, and so especially when you're creating new ways of measuring things and there aren't tools to do these things, Mike's probably done a ton of that as well. You have to.
We hear that we hear that from a lot of our guests, that coding has become more and more important for a physics undergraduate to get an actual handle on. And I mean, specifically, we've had them asking, what should they learn? So if you were to put it out to, you're speaking to physics undergraduates right now, what should they be studying? What should they learn? What should they get a handle on? They've got a whole summer to get this stuff under their belt.
Yeah, I mean, I would say, personally, I picked up Python for data analysis, but I was working with, what I was doing was, I would say, fairly straightforward, but it was like big data sets that I just needed to work and do fairly simple calculations on different columns of data and find certain trip points in the data to do certain, break up the charge and discharge cycles. I was doing thermal measurements on a cell with a different device that I was doing the electrochemical measurements on. So I needed to merge all that stuff together and then, pull some of the current and voltage data to make some kind of heat calculation and take it away from the thermo data. So, all of that, there were no tools to do that and break things up into charge and discharge. And so you can't do that in Excel unless you take your entire PhD to do it.
Right. Well, go ahead.
Maybe to tie in, I don't really care what language people use. It's like, what problems can they identify and then solve with it? Like Python's a great tool. So I've heard. I'm still using the older languages that, I guess I'm pre-Python. I haven't bothered to learn it, but at the same time, I'm coding just about every day. And it's...
Oh, really? Wow.
Oh, yeah. Like we do all of our presentation, all of our data analysis, when I'm doing a presentation now, I'm coding it just because it's faster. We have I interview a lot of people looking for co-op positions and similar. And it's like, well, I've got these skills on my resume, but then I've seen other people. It's like, well, here's what I solved, or here's this project that I made on something else. And it's that kind of thing, I think, is another way to get your foot in the door. It's like, solve a problem. Like it doesn't matter what it is, but it's just like Stephen was saying, like there are massive data sets of whatever, and then what do you get out of it? One thing I did recently with my committee work was looking at like, what are the carbon emissions around Edmonton, which has nothing to do with batteries, but it's like, okay, here's this source of carbon or CO2. Here's the center of Edmonton. How far away is it? How does that look as the emissions as a function of distance? Simple thing, right? But it's not. How to pull that data together. I won my hockey pool this year, and so I wanted to see who won the most over time. And my brother will say that he's won our pool the most, but that's fine. But it's, how do you look at a data set and then present it? That's the important thing. It doesn't really matter what language you do. Use to do that. It's that you can take a data set of whatever and make it look good or learn something from it.
Well, it's interesting as well because, in a lot, probably Mel is probably the most recent experience with this. She could probably speak to it. Is that we try to push so much about data analysis to our undergraduates, and it seems, and I understand it. I didn't want to do it either, but I mean, in terms of, we're looking at, in Stephen's case, he's almost a decade out. In Dr. Fleischauer's case, he's almost 35, 40 years away from his undergrad at this point. But he's 20 years out, and it's that kind of data analysis that is perhaps some of the most important part of science, especially now when we're sitting in an era of science where we can collect data faster than we can analyze it. We're getting close to the end of our broadcast here. We've got a few more minutes left, so I wanted to address some of the questions that we've been having in the chat before we get to it, and give our viewers an opportunity to put a few last-minute questions into the chat as well that we can get our panel to answer here. But I wanted to bring this one up, and this was one that I also had a question about. This one comes from Christian Schultz-Nielsen, and it's funny, you think about that original story I told about the frog's legs. It's kind of one of these things where it's with your battery materials. Are you engineering materials towards the end of having these properties, or are we just finding these super materials out in the wild that actually give us good energy storage and good lifetime?
Yeah, Mike, you want to tackle that first?
Sure. So lots of things exist. It's a question, like, there are lots of people that are taking materials like the membrane in an eggshell, for example, was turned into a really good electrode for certain things. So yes, there's a certain randomness. So I've got a material, I've got a big pile of it. Can I make it into a battery electrode? The flip side of it is that a lot of materials have been studied for a long time. So it's hard to do. One of the hotter things right now in lithium battery work, where it's not necessarily lithium ion, but rechargeable lithium, is just using aluminum foil as an electrode. Aluminum foil has been around for, I don't know as a foil form, but it's been commercialized for 200 years, right? It's on a commodity now. And so it's a question of how do you do the material science to understand what's going on, or the physics to understand what's going on in the material, do the engineering on how does that integrate into a manufactured product, how do we manufacture it, how long does it last? So I don't think there's an easy answer to that. I don't think things are just found and they're magic and they're good. It's kind of like I forget the analogy, it's like the overnight success over 10 years type thing. But that 10 years, sometimes 30 years, where when you see when are these materials first discovered. It's all like, I want to give credit to Professor Dahn. He's been very, very in front of things for a long time, and seeing, okay, here's a problem we need to solve. Here's a possible route to solve it. That's what's kind of out in the, I think you'd said it, out in the wild. The problems are known, or the problems are there to be identified, but the solutions are not. And it's lots of different ways to get there.
Yeah, I think one of the things that's been happening a little more recently is kind of revisiting all of these older technologies that, back then when things weren't as well understood, when you could kind of throw stuff at a wall and see what sticks, they didn't seem like viable solutions back then, and we couldn't really figure out why, all of the mechanisms that led to their demise or their explosions, happened. But now that there's a lot more understanding and fundamentals behind it, and a lot more, a bigger history of throwing things at a wall, and then understanding them, we're revisiting these things like, like solid state batteries, pushing the use of lithium metal in batteries rather than capturing the lithium ions in a more stable substance. If you can just use lithium metal and, transport the ions across and make it into a super thin sheet of lithium metal reversibly, your energy density is huge. But it comes with a lot more problems that we're in a much better state to solve right now. And I think, that's where Jeff Dahn is even going with some of his work now. There's been a bunch of anode-free papers that have come out of that lab, looking at these kind of older ideas of lithium metal in cells, and that's kind of old ideas, but new science puts behind them.
Yeah.
Well, and I think it's fairly exciting that this type of sort of the world leaders on this type of stuff are working out of Canadian institutions. It's kind of an exciting opportunity for our Canadian undergraduate students if they're looking at getting into something that they have an opportunity to be on the cutting edge of this type of thing. And speaking to this idea of being in a lab, Mel always asks a classic closing question that gives us a bit of an opportunity to chat for a few more minutes anyway. I do want to point out a couple things before we go into Mel's closing question here. One of which, again, is that coming up at the end of June, we'll be celebrating our 125 years plus one of the Department of Physics here at the University of Guelph. And to join us online for a virtual alumni week on June 25th, you can register at the address shown below. We'll have guest speakers. We'll have a chance for socialization. It's going to be, we have some fun breakout rooms planned. And it's an opportunity to touch base and to chat with some of the professors that you might have had in the past, some of the ones that are currently here, and an opportunity to network between graduates and our current students. So I just wanted to bring that up one last time. But I'll send it off to Mel. We'll give you an opportunity here to ask your closing question.
So I guess in your academic or professional careers, what has been your most exciting day, either in research in academia or in the world of batteries?
That's tough. So if I'll give you maybe some time, Stephen, and I'll answer it. So my most exciting day was when a student that I had, not formally, but in practice, co-supervised for his PhD, he received a massive award here in Alberta for being the top young promising entrepreneur. It's Dr. Ryan Tucker. So Ryan's now the CEO of a local company that I was involved with before it was a company, G2V Optics. So it was seeing Ryan be recognized for how good he was. That was my favorite day.
Aww.
It's true, though.
That's a really nice one.
That's awesome.
All right. Well, that's you've got now's your chance to impress, Dr. Glazier. What's yours?
I think I'd have to just choose two. The one would be from my PhD. I took a research trip down. Dr. Jeff Dahn's lab was, and still is, sponsored by Tesla. So all of the research is kind of done, under the funding and for Tesla's mission. And I got to go down to Palo Alto with Jeff and just go through headquarters, tour around the facility, and see all of these teams in action, just like hundreds or thousands of people crammed into all of these engineering and science offices. Everything was complete chaos and disarray, but somehow making magic happen. And it was kind of then that I went, I'm definitely going into industry. It was really cool to see everything happening and sit in on some of the meetings. But my number two favorite is when at Novonix, we started, there were three of us that kind of started up the cell pilot line there, and trying to learn how to use all of the pilot equipment and make batteries and then test them. And when we got kind of our first really good performance results that were as good or better than what we expected from the commercial cells, was a really great day.
Fantastic. Well, I guess that kind of brings us to the conclusion of our broadcast here. I'll give both you, Dr. Fleischauer, Dr. Glazier, an opportunity to plug your research. But first, I wanted to thank Mel for joining us tonight. And for those of you who frequent our YouTube channel, please get a chance to check out the Science Expert Mel videos that have been up. There's a nice new series of 4 videos that maybe the junior scientists in your life might have an opportunity to try to experiment at home. And you can do that alongside Mel. So thank you very much, Mel. We'll see you later.
Bye, guys.
See you later.
And Dr. Fleischauer, if people are interested in your research, where can they follow you? How do they look you up?
Well, I've got a relatively unique last name. I think a very good last name. So there aren't that many Fleischhauers in Canada. Certainly fewer in Edmonton. So I think I'm fairly easy to find that way. I'm with the National Research Council and the University of Alberta. I've got a webpage with U of A. Might probably be the easiest way.
Great. And Dr. Glazier, where can people follow you or find out more about your research?
There's the Novonix website, novonix.ca. And you can see kind of what we're up to there. There's actually just started a blog on some of the Novonix technology and kind of just interesting things happening in the battery field there. So you can look stuff up there. That's
fantastic. Thank you very much. So I'd like to take an opportunity to thank both of our guests on tonight's panel, Dr. Mike Fleischhauer, Dr. Stephen Glazier, and as well thank our roving reporter Mel for popping in and chatting with us. And I'd like to thank most importantly our viewers for joining us this evening. We will be continuing the summer series throughout the following months. It's looking like we'll be doing about one stream a month, so please stay tuned, and we'll be pushing that on all of our social media. If you want to follow us on Facebook, on Instagram, Twitter, or on YouTube, it's all under Guelph Physics. So please take that opportunity. And if you're an alumni, then hopefully we'll be seeing you on June 25th for 125 years plus one. I think we can end on the statement that we all know to be the case, that physics is indeed the best. Take care, everyone, and we'll talk to you soon and hopefully chat with you in July. Until then, I'm the Great Orbax, and thank you for joining us.